we are back again. So in the previous lecture, we discussed generalizations of Cauchy's integral formula. And so here is the formula that we discussed in the previous lecture, that derivatives of analytic function are also analytic, and we have this formula for derivatives, how they can be computed. Now let's look at one of the theorems that follows from this formula. So in some books it is called Cauchy's estimates. In some books, in the current Saf's book, it's called bounds for analytic functions. So here is the theorem. So let function f of z be analytic inside and on a circle CR, circle of radius r, and this circle is centered at point z sub 0, and assume that modulus of function f of z is bounded by a constant m for all these in the disk, or we can say on CR, and then we will have this estimate that modulus of the derivative is this. So let's prove it. The proof is really simple, and of course it's based on this formula. So what we need to do, we need just to evaluate f and its derivative at point z sub 0. We know that it's equal to this, so we have modulus n factorial over 2 pi I integral along CR. So in the previous lecture we were talking about just a loop C. Now we just took a specific loop, which is a circle. And then we have f of s ds s minus z sub 0 n plus 1. And let's look at what we have. So if we compute modulus of some constant times integral, so modulus of this constant would be just n over 2 pi, right? N factorial over 2 pi, because modulus of I is 1, so we will have n over 2 pi modulus of the integral along CR f of s ds s minus z sub 0 n plus 1. And now let's go back to our theorem. That's what we are given, that f of z is bounded. So then we can write less or equal n, oh sorry, I forgot here, n factorial over 2 pi, and instead of f of s we can pull out just m, so I put less or equal to, and then we have CR ds s minus z sub 0 to the power n plus 1. And we still can keep modulus if we want to. And then we can we can use two ways. So one of the ways would be that this is obviously less than r, radius of our circle, so we can pull out r to the n plus 1 as well. And then we will end up with the integral along CR of ds, which will give us a circumference. Or another way how we can proceed is to parameterize this circle and compute this integral honestly, which we did several times in the past. So let's just put it this way. Let's take r, so we will have n factorial 2 pi m, then it would be r to the n plus 1, and I can write it again, but it will be just integral along CR over ds. It would be obviously 2 pi r, circumference. So 2 pi r, and then we will end up with 2 pi and 2 pi are cancelled. Then 1 r would be cancelled, and we have n factorial times m over r to the m. And this is exactly what we wanted to prove, so the proof is done. Okay, so we proved Cauchy's estimate. Let's call it theorem 1. And now let's prove, it would be a really short proof, another theorem. Let's call it theorem 2, and this is Liouville's theorem. So it's due to Liouville's theorem. So it tells us that the only bounded entire functions, the only bounded entire functions are the constant functions. Are the constant functions. And this is really easy to see from the Cauchy's estimates, from this formula. So let's take this formula and apply it to the first derivative. So when n equals 1. So it's proof. Let's take n equals 1 in Cauchy's estimate. So then what we will get? We will get f, first derivative at point z sub 0, and that would be equal to m over r, right? According to this formula. And so what does it mean that our function is entire? Entire means analytic function in the whole plane. So we can take radius of our circle as big as we wish. So, and then what happens if we send r to infinity? Right, function is bounded, so we know that exists such a constant m, and what happens when r goes to infinity, then this will go to 0, right? As r goes to infinity, this will go to 0, r is going, and so what does it mean? So first derivative of a certain function is 0. That means that the function is constant. F is constant. So in other words, what we can see that if we have a really well behaved function that is both bounded, right? And entire everywhere. That means that this case is extremely boring. Our function is just a constant, nothing but a constant. Cauchy's estimate and Liouville's theorem give us another tool to prove fundamental theorem of algebra. So there are different proofs, so one of them could be performed using Liouville's theorem. So you know that fundamental theorem of algebra reads like every non-constant polynomial with complex coefficients has at least one zero. And from here it will follow that polynomial of degree n has n zeros. So let's write down one of the polynomials, so that would be a proof. So suppose we have polynomial p of z. It will be a function, say a(n) z to the n plus a(n minus 1) z to the n minus 1, and so on. Then second from last will be a1 z plus a sub 0. Non-constant, it means that constant is if we just have a sub 0, so we have a non-constant polynomial. So let's think of what is behavior of this function at infinity. When z goes to infinity, then this polynomial is growing. So how we can see it, let's just, here we have p at z. So we can rewrite it if we just pulled out z to the nth, then here we will just have a(n) plus a(n minus 1) divided by z plus a sub 0 divided by z to the n. We can pull this out, and then we can see that when modulus of z goes to infinity, then this would be bounded. Let's assume that an is non-zero coefficient here for definiteness. So this would be just bounded, and then we can see that p of z, when limit of modulus of z goes to infinity, it also goes to infinity. So that's what we have. So now let's prove by contradiction. The theorem says that every non-constant polynomial with complex coefficient has at least one zero. Assume that it doesn't have zeros at all. So what does it mean? That there is no such a number a that we can plug in and get zero. So function p of z doesn't have zeros. Then in this case, what can we say about function 1 over p of z? If p of z is never zero, then this function doesn't have singularities, and this function also will be entire function. So I probably should write this contradiction. So assume p of z is not equal to 0. Then we will have that 1 over p of z is entire function. So let's look at this entire function 1 over p of z. What would be the limit of 1 over p of z when modulus of z approaches infinity? if this goes to infinity, then 1 over p of z will go to 0. Then it will be 0. So if it is 0, then it will be getting smaller and smaller, and assume that we have a circle of a big radius r, where r is big. So if it is huge enough, then this would be getting smaller and smaller, and we can find such an r, exists such an r radius of the circle that outside of this radius 1 over p of z, this modulus is less than 1. Since it's going to 0, at some point it will be less than 1 if z greater than r. So what did we establish? We established that our function less than 1, it means our function is bounded outside of this disk. Now let's see what's happening inside of this disk. Inside of this disk we have our function 1 over p of z. And we know that function 1 over p of z is entire function, so it means it's analytic everywhere and inside this circle as well. So function is analytic, and analytic function is obviously continuous. So we have a continuous function. If we take it modulus, we will get a real valued continuous function. So what can we say about this real valued continuous function and given on let's say compact, given on this disk, closed disk, which is bounded because it has radius r, and which is closed, we will take the boundary. So we know that continuous function on such a set attains its maximum, so our function will be bounded. So we can find its maximum, and our function is bounded on the disk as well. So what do we have now? Now we have that our function 1 over p of z is bounded inside the disk, outside the disk, so it's bounded everywhere, and we know that our function is entire. And let's recall Liouville's theorem. So the only bounded entire functions are constant functions. From here we can immediately conclude that our function 1 over p of z is a constant function, and therefore p of z is constant, which gives us a contradiction, that contradicting our assumption that our polynomial p of z is a non-constant polynomial. This finishes the proof of this theorem. So at this moment we covered all of the materials related to chapter 4. Let me quickly summarize everything that we have discussed. So summary of the chapter. So first thing, we were talking about how to compute integrals using parameterizations, using path. Right? So you can, if you have an integral along a curve, it doesn't matter if it's closed or not, curve in the plane, then you can parameterize this curve using parameter t, which is considering a path, and then with this parameterization, suppose t runs from a to b along a segment, you can compute this integral. So the advantage of this method is that this method of computations works for both analytic and not analytic functions. So if you have a function you're not sure whether or not it's analytic, you can use parameterization. If we have analytic function, right, then we have some special results. So I mark them with 2. So if function is analytic along the curve, everywhere in this neighborhood of the curve, then we can use fundamental theorem of calculus, right, which means that antiderivative exists and we can just compute an antiderivative and evaluate it at endpoints. Right, so the integral then does not depend on the path, only on initial and terminal point. Then we discuss Cauchy's theorem. If we have a closed contour and function is analytic everywhere on the contour and inside, if no singularities inside, then we have 0. If we have singularities in the integrand, but special type, restricted, later on we will talk about more general case, but if we have analytic function f, which is divided by z minus z sub 0, and here I wrote the generalized version of Cauchy's integral formula, then this can be computing using derivatives. And it also shows us that when we are dealing with analytic functions, they have derivatives of all orders. So here n is 0, 1, 2, 3, and so on. Then if we have 2 paths, and if we're talking about a more general, not simply connected domain, but if we have 2 contours that are homotopic to each other, which means if one contour can be continuously deformed to another contour, then we can change the contour. Integral will not be changed, the value of the integral. Then we discussed Cauchy's estimates for derivatives of analytic functions, and Liouville's theorem, which is related to this, which can be stated as if you have a bounded function and addition, your function is entire, then this function is just a constant. And another thing that was that followed from Liouville's theorem, we gave one of the proofs of fundamental theorem of algebra. So our chapter is covered. Thank you.